Today, we'll be exploring the basics of the golden ratio, the Fibonacci series, and the mathematics, science, and aesthetics of it in nature and design. We'll also take a look into why we see the golden ratio so often. Break a line into two separate pieces, with a shorter piece and a longer piece, such that the ratio of the longer to the shorter is the same as the ratio of the whole line to the longer. This ratio is called the golden ratio, or as it was known hundreds of years ago, the divine proportion. This ratio is approximately 1.618, as you can see in the animation. We call this capital Phi. If we try to calculate this value exactly, we can take the initial condition and try to solve it. The ratio of A to B is equal to the ratio of A plus B to A. So what happens if we substitute B is equal to 1? We get A is equal to Phi, which means our equation now turns into Phi is equal to 1 plus 1 divided by Phi. Since we know Phi is not equal to 0, it's okay to multiply both sides by Phi and get the quadratic equation Phi squared is equal to Phi plus 1. If we plug this into the quadratic formula, we find out that Phi is equal to 1 plus or minus the square root of 5 divided by 2. So now, we actually have two solutions to our original problem. However, since we multiplied both sides by the unknown, we might have created a new solution. It turns out this is not the case, as we can see by plugging our new solution into the original equation. The second value is called lowercase phi, and is approximately 0.618, or surprisingly, capital Phi minus 1. So capital Phi minus 1 is equal to lowercase phi. Can you think of a reason why this might be true? Give it a try, and then continue watching. The statement that capital Phi minus 1 is equal to lowercase phi can be easily shown if we take the solutions of our quadratic and then subtract them. Then square root of 5 over 2 cancels out, we are left with 2 divided by 2, which is equal to 1, thus proving the equation. Another interesting correlation between the two phis is that lowercase phi is equal to 1 divided by capital Phi, and vice versa. To show this is just a little bit trickier, so let's do this together. Let's take capital Phi and write 1 divided by capital Phi, so that 1 divided by 1 plus root 5 over 2. To get rid of the root, we can use a third binomial formula and expand the fraction by 1 minus root 5, thus giving 1 minus root 5 over negative 2, which is equal to 1 plus root 5 over 2 minus 1. Which is equal to Phi, as we have shown before. Thus 1 divided by capital Phi is equal to lowercase phi. Let's go back to our initial picture where we simply divide a line by the golden ratio. This line has a special name, called the golden line. If we now set our unit length to the smaller side, we have split our line into two parts, with length of Phi and 1. Now let's create a rectangle with these two side lengths, Phi and 1. This is called a golden rectangle, and it has an interesting property. If we cut out a square with length 1, we create a new golden rectangle. If we remove the square, we subtract the side length 1 and are left with a new side length of Phi minus 1 and the old side length of 1. Since Phi minus 1 is lowercase phi, and the ratio of Phi to 1 is the same as the ratio of 1 to lowercase phi, we still have a golden rectangle. Let's continue on with the pattern a bit. Again, take the rectangle, scale, and rotate into place. But what can we do with these golden rectangles? Well, we can make a spiral by drawing a quarter circle in every square. This spiral, if continued infinitely, is called the golden spiral. It's a pattern seen many times in nature. It's beautiful and yet very simple to construct. Start with a sequence 0, 1, and continue such that the next number is the sum of the previous two numbers. So 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, and so on. Mathematically, this series can be written like this. This is known as a Fibonacci sequence, coined by the Italian mathematician Leonardo Fibonacci, who was only named Fibonacci centuries later. But what does this have to do with the golden ratio? Well, surprisingly, the n plus 1th Fibonacci number divided by the nth one approximates a golden ratio better and better as n increases. Or more formally, the limit of f of n plus 1 over f of n, as n goes to infinity, where f of n is the nth Fibonacci number, equals phi. But why? To prove this, we can consider our term f of n plus 1 over f of n. By definition, this is equal to f of n plus f of n minus 1 over f of n, which we can rewrite as 1 plus f of n minus 1 over f of n. Now, let's define x is equal to the limit of f of n plus 1 over f of n, as n goes to infinity. For a clear proof, we now need to show the ratio actually converges. Unfortunately, this is a little trickier and therefore we won't go over it here. However, we now see that f of n minus 1 over f of n is equal to 1 over x as n goes to infinity. So plugging that in, we get x is equal to 1 plus 1 over x. Does this seem familiar? Well, this is exactly the same equation as we had for the golden ratio. Therefore, we have now shown that f of n plus 1 over f of n equals phi when n goes to infinity. Fibonacci came up with a simple problem called Fibonacci's rabbits that details an estimate for the growth of rabbit populations. This model assumes that a newly born breeding pair of rabbits are put into a field, each pair mates after 1 month, produces another pair after their second month, and never dies. Fibonacci posed the puzzle, how many rabbit pairs will there be after a year, or more generally, after n months? At the end of the first month, they mate, but there's still only 1 pair. At the end of the second month, they produce a new pair, so there are 2 pairs in the field. At the end of the third month, the original pair produces a second pair, but the second pair only mate to gestate for a month, so there are 3 pairs in all. In the end of the fourth month, the original pair has produced yet another pair, and the pair born 2 months ago also produces the first pair, making 5 pairs. The answer to the number of rabbits after n months is f of n, where f is a Fibonacci sequence. Due to the nature of the problem and adding a new pair after 2 months, we add the second to newest number each iteration, thus creating the Fibonacci sequence. While the sequence isn't actually very accurate for rabbits, it's actually highly accurate in predicting the number of honeybees in a population, since honeybee populations observe the following rules. If an egg is laid by an unmated female, it hatches a male or drone bee. If, however, an egg was fertilized by a male, it hatches a female. Amazingly, the Fibonacci sequence still predicts honeybee populations realistically enough to be useful. We find the golden ratio all across the natural world. We see golden spirals in plants and flowers, golden rectangles on the faces of animals and humans, and varying sizes from the microscopic DNA that determines who we are to the spirals of the galaxies. But the big question is, why? We see the golden ratio incorporated into design frequently, specifically architecture, artwork, photography, and logos. We see the golden ratio in music. The very backbone of our musical language counts in octaves and uses perfect fifths. This is the human heartbeat. Does it look familiar to something we've seen before? It's fairly similar to the Fibonacci series convergence, which is how the ratio of one Fibonacci number to another converges towards the golden ratio. We see the Fibonacci numbers in flower petals and tree branch numbers, in pine cones and leaves. Now let's delve into why. This is a very nuanced and complicated question, and varies depending upon what location of the golden ratio we're discussing, but let's tackle a fun one. If you were a plant, what angle would you rotate your leaves or petals every generation to maximize the amount of sunlight? Pause the video and think about it for a few minutes. So the answer to our problem is the rotation with the least overlap in order to maximize the amount of sunlight. But what rotation is with the least overlap? It ends up being 137.51 or 222.49 degrees. But why? We want the most irrational ratio to 360 degrees in order to have the least overlap after any given number of iterations of new leaves. The most irrational ratio is a golden ratio, and 222.49 is 360 degrees divided by phi, or 360 times lowercase phi, and 137.51 is 360 minus 222.49. So that answers why we see the golden ratio in flowers, but what about everything else? Seashells, our faces, our very DNA, why? One answer that covers a lot of cases we see in nature is that nature grows in specific patterns, which are often described by fractals. The golden spiral is a pattern based in a ratio, and easy to nature to appear by both simple cells following simple commands to large-scale patterns emerging over thousands of years in galaxies. The golden ratio is the solution to a simple quadratic equation, x squared is equal to x plus 1. Numbers that are solutions to simple equations tend to appear more frequently. Occam's razor explains that solutions that are the least complex are the most likely, and I believe in nature, particularly systems guided by the laws of physics, chemistry, and biology, that this can certainly hold true. Another interesting idea is that we see it in some places in nature, therefore it's seen as attractive, fitting, or even normal, and therefore has been subconsciously selected for over thousands of years of evolution in many different species when selecting a normal or healthy-looking mate. One more answer is that it doesn't. It doesn't appear as often as it may seem. Data is often cherry-picked, people want to see it, confirmation bias, and quite simply people online wanting clicks, views, attention, and therefore money, can bring outlandish claims to fruition for their own personal agenda, or even simply for lacking of knowing better. We do, however, see the golden ratio in some places in nature, where the solution to a problem, and thousands of years of evolution, have slowly caused the organisms that are most fit for their environment to have an advantage and reproduce, per evolution. We've already seen this in flower petals and plant leaves, but let's explore one more interesting one. Falcons have eyes on the sides of their heads. They don't fly straight at prey, because they wouldn't be able to see it. So a falcon must tilt its head to the side to see clearly with one eye. But this tilt would decrease the streamline efficiency. So instead, they evolved to descend on their prey in a spiral pattern, to always keep their prey in eye line, and descend quickly yet energy efficiently. And it turns out, the most efficient way for a falcon to get to its prey is by following the golden spiral. This isn't a coincidence, but rather due to being mathematically optimal for its situation, and has evolved after thousands of years of brute force. Falcons, of course, didn't take out a pen and paper and compute this. Many falcons over many years descended onto prey in many ways, and the most efficient ones obtained their prey and survived, and passed on their genes. The golden spiral just happens to be the most mathematically optimal solution for their problem.